Today, I'm talking about something that we kind of loosely call a Hydra architecture for orchestrating machine learning across regions and clouds and various clusters. Don't spend too much time thinking about the term Hydra architecture. It's just meant to paint a picture. We're going to go into some history of ML execution infrastructure or distributed ML infrastructure, and hopefully help people think about how to architect their ML systems better. As Kiara mentioned, I'm Donnie. I'm the co-founder and CEO of Runhouse. I was previously the product lead for PyTorch at Meta. I worked with hundreds of ML teams, led some large platform re-architectures for Meta's internal ML platform, worked with the open source PyTorch community extensively across startups and large enterprises, cloud providers, et cetera. So a lot of the opinions that you'll hear here were formed just over those experiences working with a very diverse set of ML teams. And just to not bury the lead about Runhouse, we're a distributed computing platform for enterprise machine learning. We say enterprise machine learning to specifically distinguish it from like kind of AI lab style machine learning, like training one big model, but rather, training one big model every few months compared to training many little models, modeling first party data and problems, which we kind of think of as more like commercial ML. We're New York based and founded in 2002. So just to kind of set a little bit of context for how we think about ML infrastructure, we take a lot of inspiration from the data side. And on the data side, we see kind of pre-OLAP databases and post-OLAP databases as two like very, very distinct times for data work. Before OLAP databases, you could run, as an individual data engineer, data scientist, or analyst, you could run SQL, single node quite easily. But anything that was larger, anything that required data that was too large for a single node or compute that was too large for a single node, you needed to do infrastructure stuff. That might mean staffing a team to manage your Hadoop clusters, and then even having to massage your queries and break them up to actually get them to run on your infrastructure. Often that meant working really closely with the infrastructure team. And then like post-OLAP in the quote unquote modern data stack, with all the baggage that the term carries with it, you just write SQL queries, you send them off at your platform, and you don't really have to think that much about how the SQL queries are formed unless you're like cost conscious. The platform just does magic, executes your SQL query for you on ephemeral or cloud compute that is maybe not directly exposed to you. And it gives your infra teams a way to manage and prioritize that compute in a way that abstracts it away from you. So abstracting the infra complexity was kind of really transformative for people who could write SQL queries and even very sophisticated SQL and chain them together through tools like dbt, but really didn't want to have to think about infrastructure whatsoever. ML just doesn't have any of this. ML engineers and data scientists typically spend, or rather at a typical company, you see 50% of overall like ML engineer and data scientist time wrestling with infrastructure or doing infrastructure busy work or thinking about the infrastructure, trying to get things to run, especially when you get up to a point where you're trying to do something slightly new. Right? Like introducing slightly more sophistication or adopting a new distribution system or something like that, you end up spending a ton of time with the infrastructure, or just dealing with faults. Something breaks. Debugging Airflow pipelines is kind of a common way that people talk about this anti-pattern, but there are a million ways that it shows up. And you actually hit multiple walls scaling up. You're going from just a few models that can be like manually managed to having to work with having to centralize your platform to accommodate like a diversity of models or methods across multiple different teams, or even just like walking up the scale chain, going from like CPU training to GPU, single GPU to multi-GPU, single node to multi-node, et cetera. So I want to just give a little bit of a history into why the ML world actually looks this way, and even just kind of elaborate on the term ML platform, like talk about the systems that are supposed to be doing this for us. So originally, ML platforms had this sort of point solution or grab bag feel to them. It was sort of an answer to any question that a team might have about how to do X in ML, but it wasn't really super elegant as far as how it answered that question. So the platform itself would just have something for inference, something for launching notebooks, something for doing training, something for hyperparameter optimization. You could kind of just expand this out so that no matter who you were talking to, if they had a problem, you could say, hey, we have a production ready thing that will do this thing for you. But all those point solutions were actually very opinionated, right? Like you're just kind of constantly responding to feature requests. You're going to end up building a pretty opinionated platform. People want to stray from that. they're going to have to sort of crash out of the system into some sort of homegrown infrastructure. And a lot of companies aged out of these kind of opinionated point solution based platforms around like 2020. Not all, there's still probably 30 to 50% of enterprises that are actually doing ML or on some sort of platform to get through the experimentation stages and just get something working. But many companies, especially as they accommodated multiple teams with multiple types of methods, kind of aged out of this into something that was a little bit more custom. And then the kind of more custom solution often meant having to build something from scratch. And building something from scratch often just meant that you were satisfied just being able to get your actual machine learning systems working. And that generally means production. So if you had some sort of recurring training pipelines or model serving production, you were standing up production systems like Airflow or pick your favorite orchestrator or experiment management systems to be able to track executions for reproducibility or lineage, and serving a serving system or like Kubernetes to kind of manage the underlying execution of all this. And then if you were satisfied with actually getting these things working in production, or rather if your team actually managed to get all this stuff working in production, you probably just needed some sort of stopgap to be able to give the researchers a way to iterate and do the research without having to do all their work directly on those production structures. Like, you don't want to actually write all of your day-to-day machine learning experiments, do your debugging and iteration, et cetera, strictly inside of Airflow. So you ended up with this like pretty fragmented stack between research and production. And every time that your researchers were done doing their experimentation in whatever kind of toy research environment you gave them, like hosted Jupyter notebooks or something like that, then you'd have to take like 6 to 9 months to translate it to the production side. And then after it's been translated to production side, it's not exactly very iterable or debuggable. So we see a lot of teams spending a lot of time on actually just fault tolerance because they get training failures or pipeline failures, and then there's no there's no first class way to actually directly debug these systems because you kind of execute through deploying updates to the production stack. And they also come with a degree of rigidity because even the orchestrators themselves have many fundamental assumptions about them, the structure of your programs, et cetera. So the latest evolution of this was to choose a sort of unified runtime, or rather a kind of walled garden system that you give to both your researchers and you use in production, such that the code itself is identical between research and production, and there's no research production migration process or gap, but you can directly expose your researchers to debuggable, iterable environment with that runtime. And then on the production side, anything that you run in production will also have that runtime enabled. So the big and Ray has been a significant enabler here. We've seen a lot of companies adopting Ray for this particular reason. But there are also other kind of walled garden systems like Snowflake and Databricks have their own kind of ML solutions to be able to do research and production ML, but with varying different pieces of the feature sets. The big downside here is that the walled garden also means that all execution has to be in platform, meaning that everything that your researchers do have to actually be on an environment or in an environment in which that runtime is enabled. So you need to be like SSH'd into your Ray cluster or have like special IDE extension to connect into the Ray cluster. And then everywhere in production where you're running ML code, you need to not just be running on a normal Airflow node, you need to be running on a Ray cluster Airflow node. And it's an infrastructure left to enable all this. And also maybe Ray isn't the only distributed framework you're supporting. Maybe you also have some Spark, maybe you have PyTorch distributed, et cetera. So it's not the same thing as submitting SQL to Snowflake from afar. It would be like if everything that you did had to be kind of developed in Snowflake and then triggered by like a custom SQL statement that ran the thing that you built fundamentally in Snowflake. And the kind of remote first experience was not directly supported. And then also there is some platform opinionation and rigidity. You could see Ray as a universal runtime or Spark as a universal runtime, or you can see it as like a handy distributed DSL for the times that you need it. And the difference is whether you force that every environment is using Spark or Ray, or you kind of surgically use it wherever it's actually helpful to you. And the difference is whether you need to do a big code lift, whether you have cascading failures, if the Ray cluster or the Spark cluster fails, whether you can support a certain degree of heterogeneity in the jobs that you run, whether they have to, whether you can accommodate like multiple types of distribution within the same job, et cetera. And I'll actually just call out that one of the maybe not so intuitive implications of this is that because you're running all of your machine learning code on a Ray cluster or a Spark cluster, what that really means is that the use case of having multiple different clusters within the same workflow is not super directly supported. It's actually, basically, if you're using the Ray client, let's say, you can't really be connecting to multiple different clusters simultaneously. And if you were trying to work across multiple clouds, or you're trying to work across, let's say, multiple regions, you need to actually be connecting to multiple clients. It's not really a good idea to wire up some massive Ray cluster that traverses clouds or clients. Certainly, that would be a pretty challenging thing to do, and I think it'd be pretty brittle. So we generally think that an ML platform, especially in the world where you have very rich code completion available to you, we generally think that ML platforms should make it so that the experience of developing ML systems is sort of like the same way the experience of developing SQL-based systems, where the code itself, there's a ton of open source example code. You can get quite a bit of help, and you can start from some pretty rich use cases already developed out in open source to actually unblock a new level of sophistication in your ML, or unblocks a new use case that you're prioritizing. And then the only two ingredients that you really need are the data and the compute. And so we're not really talking so much about the data. We're not really solving kind of the fundamental data problems here. We take advantage of like existing data systems for like streaming in data, or for warehousing it, or meaning, whatever, unifying it so that it's accessible from wherever you're doing your ML stuff. But we think of like what an ML platform should be is actually just providing you with that compute environment where whatever example code you manage to put together, or pull from open source, or whatever ML code you manage to develop, the part of it where you actually get it up and running, especially with distribution, is not really your problem. So we sort of refer to this as a Hydra architecture. There's a very particular reason why, where specifically the driver program, the thing that's actually running the ML, that has, like, let's say, the ML logic, the Python code for the ML methods proper, can just dispatch to the places of execution, pools of compute, where it's going to actually run the heavy components. And what that means is that you don't need to adopt a unified runtime, meaning that everywhere that you execute needs to be a Ray cluster or a Spark cluster, but rather everywhere that you execute is basically just Python. And then you can dispatch to wherever the scaled compute, or dispatch to the platform which contains the scaled compute for executing the heavy parts of your ML programs. And that actually makes the runtime fully generic. The runtime itself is truly just arbitrary Python. So the thing that you dispatch is arbitrary Python, and the place where you dispatch from is arbitrary Python. And the thing that actually enables this is this like Hydra architecture where you split the heavy execution from the kind of driver program, the thing that's actually just running the underlying Python, which contains the ML methods. So we basically feel that the ML platform should provide that abstraction that makes it really easy and intuitive to dispatch your programs to wherever the heavy compute is. And it has to be flexible enough for any ML task, right? If it's opinionated, if it has any limitations about what you can actually do, then all of a sudden it doesn't feel like this magic big computer that you can dispatch things to. It feels like a prescriptive system that somebody kind of thought of some things you might want to do and then gave you a simple API to call them. But if you want to deviate from that, then you're going to be stuck. So we also refer to this Hydra thing as like platform as a runtime. So, as opposed to execution via deployment, which is kind of the standard for ML workflows. So, when you run an Airflow pipeline, you need to actually rebuild and redeploy it. Or when you want to test out a new model service, and you don't have the local compute to actually run the model, then you're going to rebuild and redeploy it every time that you make a change. So that is a major anti-pattern. It makes iteration and debugging incredibly difficult. It makes research production incredibly slow. But if you have this platform as a runtime concept where your core driver, which is the thing that's actually your service or your pipeline or your CI system, whatever is actually running Python, and you separate that from the platform, which is where the heavy execution is, then even when we're talking about running those things in production, they're still accessing the platform execution the same way that you would be locally. And so you have a kind of a unified runtime in that way. So the big benefits of this approach are, one, dramatically better developer experience. So you just write regular code, and your code utilizes the platform for distribution and execution, just like it will when you run it in production, and you get full iterability, debuggability that you'd be used to just writing code locally. And there's no opinionation about where you write your code. You can use an IDE, you can work in notebooks, anywhere that basically runs Python, this will work. And we didn't really, invent that model. It's actually the way that you might be used to interacting with your platform if you use Databricks Spark or Spark Connect. You just in code launch your Spark clusters from anywhere, do your work with the Spark cluster again in code from the remote environment, and then you shut it down when you're done. The only problem there is just the opinionation of Spark. If you remove that opinionation, you can basically and you can do anything that you want. Then it's quite an elegant model for the developer experience. And then fast research production, as I mentioned, because of this split between the driver and the platform execution, you don't really need to translate anything to go to production. You just push to production in the same way that the rest of the world pushes to production, which is using version control and feature flags and things like that. There's no ceremonious lift to translate to production. You just need to get your systems working and make them robust and iterate them, and then once they're in production, and then push them to whatever you consider to be your production environment, is the branch, the feature flag, whatever. And then certainly if something breaks in production, or if you want to change it, you also don't have to translate it back. You can just run it locally and iterate, reproduce your bug, or implement your experiment or your tweak or whatever that might be. There's also a significant cost advantage here, which is that you can be really surgical about the types of instances or the type of compute that you utilize within the platform from within the driver. So right sizing instances and having really fine grained control of the execution is a big benefit. We see people tend to save around 50% using Runhouse compared to a kind of platform in the box solution like SageMaker or Vertex. The system is natively multi-region, multi-cloud, or hybrid cloud. So you can take advantage of any discounts or cloud credits that you might have without moving your entire stack around. Even from within the driver program, we've had users who just, in a day, maybe their driver is running in AWS, or maybe it's like an Argo pipeline or something like that, and they're launching trainings using Runhouse. I'll get back to the structure of how Runhouse actually works. We're using this Hydra architecture in, let's say, AWS also, and then just one day they'll decide, actually, I want to launch that training in GCP, and everything just flows normally. So that's another major benefit. The ability to admin prioritization and limits, right? Centralizing the way that you actually access the compute is a major benefit. Snowflake or Databricks and other compute platforms do this too. You just have a unified place to set prioritization, pre-configure the compute so that people have even less to think about when they launch it, and manage the compute, turn off boxes, set auto stops, etc. And then also the system is future-proof. So not having any migration costs when you adopt new frameworks or tools or infrastructure, because the platform or the choice of machine learning methods are completely decoupled from the choice of the compute itself. That's a huge benefit, right? Like your driver program barely needs to change if you decided that the thing that you were running inside of the remote section of the program was PyTorch versus TensorFlow, or Spark versus Ray, or Dask, or whatever, or even just arbitrary Python dependencies going from CPU to GPU just means like requesting different resources up from the platform when you're actually at execution time. So I've been kind of just leading up to or giving kind of a high level description for the design considerations for Runhouse, but this is kind of exactly how we've architected the system. So it basically allows you to dispatch arbitrary ML code to be distributed and executed. It's running entirely within your own infrastructure. It's not like a cloud or kind of repackaged compute solution. That was also design consideration from day one. So that means like any hardware, any Python code, any distribution that you want to include in the code that you're dispatching up to the platform, you can run from inside of CI/CD or orchestration or any kind of DevOps toolchain you already have in place. It's like incredibly undisruptive to whatever code you already have. And the compute and data remain entirely inside of your own clouds. The overall experience is designed to have fast enough iteration for research, but also be fault tolerant and robust enough for production. This is also just a matter of making the system good at unifying that research and production fragmentation. And I'll just as a high-level case study, we had a team who were running hundreds, or we were talking to a team who were running hundreds of trainings per day, and they were running on SageMaker, but they were spending all their time basically debugging breakage in their pipelines. They went from about a 40% failure rate to like less than 0.5% using Runhouse, because the system gives them so much more control over how they interact with the remote compute in Python. And their compute costs went down dramatically. And they went from like a 2-hour debugging loop, again, executing through deployment, to just seconds being able to rerun their code locally. And then Runhouse is also a true platform as a runtime, meaning that you can execute your ML methods from anywhere, just like Spark or SQL. So you just dispatch with the system, you specify how you want us to distribute it, we automatically distribute it for you and execute it for you. So there's no disruption to your developer experience to be able to use this runtime. There's no code migration. It uses your existing code and dispatches that at the platform. And there are no cascading failures. So you don't have to worry that because you're interacting with this complex remote compute, that your driver program is sort of coupled it to any failures that happen in the remote compute. Failures in the remote compute, you can just catch them as exceptions inside of the driver program, and that actually makes fault tolerance and debugging dramatically easier. I kind of alluded to the overall architecture for how this works, but basically the Runhouse cluster, when you're interacting with the platform, you request your compute and the Runhouse cluster is allocated for you, and then you can interact with it from inside of Jupyter or an Airflow node, and you could be utilizing like normal shared team code throughout all this. It's all basically mounted up onto the cluster or synced up onto the cluster automatically when you're dispatching things up. So you don't have to be kind of writing temporary code in a Jupyter notebook when you're interacting with a remote cluster. I'll just show you briefly how this actually looks in terms of the code proper. So if I had, let's say, train PyTorch function, so this is just like an arbitrary function that I imported above, just didn't show it here, just to be succinct, but I could have written this fresh, and it doesn't have to have any particular structure. It doesn't need isolation in terms of imports. It doesn't need to be serializable or anything like that. I can take this train PyTorch function, specify the compute that I want to send it to. So I just want to send it to one A10 box on AWS. And then I can call train PyTorch.toGPU, and I get back a PyTorch. I get back a callable that's identical to my original function, but it's going to be run over RPC when I actually call it. And in the process of sending it over, I also synced over whatever code is necessary to run it. And then I can just call it natively, just as I did my original function. And then we can also do the same thing, but specifying more complex distributions. So in this case, I didn't actually distribute the PyTorch code, but I could also call .distribute and then specify PyTorch and specify my replicas, and it would automatically distribute it with PyTorch distributed. And here you can see that we're doing the same thing with Ray. I'm just calling a function that uses Ray-Tune to do hyperparameter optimization, dispatching it to the cluster and calling distribute Ray. And that actually wires up the Ray cluster, manages it, streams back logs, manages the dependencies, things like that. All the complexity of having to adopt Ray as an organization is hidden under this .distribute Ray business. And the Ray cluster itself is ephemeral. You can destroy it, restart it, etc., without even having to restart the cluster proper. We keep things like pretty isolated. You can send multiple different functions using different distribution to the same clusters. To the same cluster. It's all meant to be extremely flexible. We also provide pretty rich tooling out of the box for you to be able to observe your clusters and share them with other people. It's all meant to make this feel like a unified place to actually access your compute. Yeah, and that's Runhouse, and that's kind of the high-level architecture that we've seen work well for teams kind of moving towards increased sophistication in their ML stacks.